Hello, everybody. Welcome back to Calculus. This time we are going to study section 3.3, different rules about differentiation. We have already established what a derivative is at a point and as a function. And now we are going to learn different rules on how to find those things. And after this section, you will be able to find the derivatives of many functions very, very quickly without taking the limit as h approaches 0. Okay, so let's get started on section 3.3. I have to warn you, this section has a lot. Okay, so just be aware that this is a long section and you would want to learn this section very well so that you can differentiate various functions for the rest of the semester and for the rest of your calculus sequence. All right, let's get started on section 3.3. So this is the section that we have been looking forward to for a while now. You know, you learned about the derivative at a point. You learned about derivatives as functions. Okay, now we are going to give you a whole lot of rules, the theorems, if you will, to use in order to differentiate various functions. All right, so we'll get started with the very basic ones. All right, number one. Okay, so I will call this first part basic rules. I will give you a few. Now remember, we write this derivative as dy dx, okay, or d dx of the function, whatever this function is. Okay, so and this is going to be quite useful, yeah, I guess you can use y for this, but it's going to be quite useful because here, let me just tell you why. If f of x is a constant, what do you think the derivative is? Remember, the derivative represents the rate of change, which is also the slope. The constant function is, of course, a horizontal line. So the derivative should be what? 0, right? Okay, and it turns out to be true. Now, this whole thing can be written, remember I said this is in a nice notation, this whole thing can be written very succinctly this way. d dx of a constant function is 0. Okay, so this is why that notation is, fairly nice, because you don't have to spell out in if-then statement as I did here. Okay, so how do I prove this? I guess it's really easy, right? You assume this. Oh, what's the derivative? It's the limit of, as h approaches 0, of f of x plus h minus f of x all over h. But remember, f is constant here. So this f of anything is just c. And f of x is, of course, c. And this is simply the limit as h approaches 0 of 0, which is 0. Done. No problem, right? So if you see a constant, then the derivative is just 0. It just disappears when you take the derivative of any constant term. Okay, so the second one, this is super important. In fact, it's so important, it has its own name. It's called the power rule. What in the world is the power rule? If f of x, this is the one that you will be using all the time, okay? And we have already used or seen maybe 1 or 2 or 3 examples of this before. If f is x to the nth power, its derivative can be obtained by moving this exponent to the front as a coefficient and x to the new exponent, which is 1 less than the original exponent. So the derivative is n times x to the n minus 1, right? There's another way of writing this, of course, using the notation I was talking about, the differential operator notation. This says the derivative of x to the n is n times x to the n minus 1. All right, so let's see how this works. Okay, now This was actually the proof of this, right? So the proof, before I go into the proving of this, and this proof will be involving, a lot more involving than the first one, but that's okay. I want you to see this. It's not necessary that you memorize this proof, but I want you to see where this comes from. Like, sort of strange that, you know, to move the exponent to the front and so on. Recall Pascal's triangle and the binomial distribution. So it's 1, 1, 1, 2, 1, 1, 3, 3, 1. Oops. This triangle of numbers is called the Pascal triangle, or Pascal's triangle. Oops, that's not right. Okay, and these are called binomial coefficients. All right, and so in the nth row, this is the third row, the nth row, the kth number is called n choose k, and this is n factorial n minus k factorial. You don't have to really know this, but you may have seen this kind of thing. All right, so these are called binomial coefficients. This is actually the number of ways of choosing k things out of n things without replacement. Okay, again, you don't need to know all of those details, but there is a thing called a binomial theorem, which tells you how to expand a binomial to the nth power. Okay, so the first one is, of course, this number, the initial number in every line is 1. So the first term is going to be a sub n, but the second term is going to be this, the second number you see here, which is it's n over, it's n1, but it's actually n. And so n times a to the n minus 1, b to the first, and so on. The exponents of a starts with n and goes down by 1. The exponents of b starts with 0. See, b to the 0 is 1, so you don't see it here. But and then increases by 1. Right. So the next one is going to be n choose 2. So that would be the third number you see here. So if it's the sixth power, sorry, if it's the fourth power, it'll be 6. Fifth power, it'll be 10, and so on. And then a n minus 2 b square plus, and so on. And then at the end, or toward the end, you will see n a b n minus 1 plus b to the nth power. Okay, this whole expansion is called the binomial expansion of a plus b to the nth power. And that's what we unfortunately will have to use. But it's fortunate that we do have this theorem, right? Okay, so this becomes the foundation for proving the power rule. Let's go ahead and try this. The derivative defined as the limit as h approaches 0 of f of x plus h minus f of x. By now, you may be able to just spit this out. Okay, now this is the hard part. The next step. Here, f of x is x to the nth power, right? It's the power function. So this is where we will have to use the binomial theorem when you have to raise x plus h to the nth power. Okay, and it looks, the next line is going to look horrendous. All right, so just be warned, because you know, it's going to look like that. So how do you expand this? This is exactly where we apply the binomial theorem. So the first one is going to be x to the n. Next will be n, and this is actually n choose 1. Okay, in this notation. Oops. So it's n times x n minus 1 h plus, and the next one will be n choose 2. This is the third number you see in line n of Pascal's triangle, x n minus 2 h square. That would be this term here, right? Plus, and you just keep going until second, well, let's write down the last two terms. It'll be n, and this is, by the way, n choose n minus 1, which is the same thing as n choose 1, which is n. And then you have x, and then h to the n minus first power. And then the last one will be h raised to the nth power. Okay, this whole thing, maybe I should color code this. This whole thing is this entire thing, which is the expanded form of x plus h raised to the nth power. Now, I still have to subtract x to the n, okay? And I have to put all of this over h. Okay. Now, I don't know if you have ever seen a bigger fraction or longer fraction. Certainly, this is probably one of the longest. Okay. Maybe you'll see even longer ones later. I don't know. All right, now this looks terrible, and you may want to say, well, forget this, it's too much, is it? Well, okay, notice here, xn gets canceled because you see that at the beginning and at the end. And what's interesting is you see this h here, the second one has h squared, the next one will have h cubed, and all of these terms left behind will have at least one h in it, which is great, right? Because you wanted to cancel that h in the denominator. So this is what happens. You factor out h, nx to the n minus 1. Next one will be n choose 2 x n minus 2 times. Now I'm taking out one of these h's, so you will just have h. And then this will become nx h n minus 2 because I am removing one of these h's. And then this becomes what? H to the nth power means h multiplied together n times. I am factoring out one of those h's. So this h becomes hn becomes h to the n minus 1. Close parentheses. Wonderful. The bad person has been eliminated. Okay, I couldn't just plug in h is equal to 0 because of the 0 denominator that it would have produced. But now that the h in the denominator is gone, this is what you see. All right, so now you see what's left here is you have h here. Every term except the first term has h in it. Okay, all terms with h. Okay, so a bunch of these terms, except for the first one, maybe I shouldn't say all, just have a lot of terms. A lot of terms with h in it, right? Okay, so that's I should say it's the limit as h approaches 0 of this. But remember, now you can plug in h 0 for h. So all of these terms will approach 0. And so what's left is n times x to the n minus 1. Exactly what I said it's going to be. That's the derivative of the function x to the nth power. This is so nice, okay? Because in the past, even as late as recently as the last section, we had to find the limit as h approaches 0 of this and that, right? So now we can easily do this. If the function is x to the 5th, guess what the derivative is? 5x to the 4th. All you have to do is to take that exponent, write that in the front of the expression. So if you start with x to the 97th, I am not sure why you would want to differentiate this, but you can easily differentiate this without taking the limit as h approaches 0. This is what? 97 times x to the 96th power. Sort of magical that it could be so easy, but that is the derivative of a power function. Well, now the thing is, I didn't tell you what n is, right? Let's just assume, because we proved this theorem using, this power rule using the binomial theorem, we assume n is a positive integer. Okay, so n is a positive integer. N could be 1. Okay, if n is equal to 1, you have x, and the derivative of x is simply x first becomes 1 times x to the 0th, which is just 1. So the derivative of x is equal to 1. So this works even if n is equal to 1, certainly works when n is equal to 2, 3, 4, or any other positive integer. All right, cool. So that was the second. All right, number 3, the sum and the difference. So theoretically, you also have to prove these things carefully. You know, if you have to have mathematical rigor to back up everything you say, but I think you can easily say that the derivative of the sum of f and g is f prime plus g prime. Now, why is this true? I'm not going to give you the proofs of all of these. The proof is actually, it may look messy, but it's actually very simple. And because remember, the derivative is actually a limit, right? But we had this kind of thing for the limit. The limit of a sum was the sum of the limits. So for the same reason, the sum of the derivative of a sum turns out to be the sum of the derivatives. And if you have the difference of two functions, differentiating that would yield the difference of these two derivatives. So that's pretty easy. Now, for this one, I use the prime notation, but I can also write it this way. This is d dx of f plus or minus d dx of y, if you prefer this notation. You probably don't, so I'm not worried about this. Okay, number 4, the constant function, constant multiple. Okay, this is also easy. If you have k, a constant, you know, like 5 or negative 17 or something, k times f, if you take the derivative of that, you just get k times the derivative of f. So you can move that constant out to the front, all right? The notation using d dx will look like this. D dx of kf, a new function, which is just the constant multiple of f by k, is going to be k times the derivative of f. All right, so these again are very intuitive and clear, easy to understand, and these are true simply, almost trivially, because of those properties of the limits. All right, so these actually give us a lot of tools. Okay, so let's say I give you a question like differentiate the following function. F of x is 3x fourth minus x cubed plus 5x minus 26. Okay, just made this up, by the way. All right, so what is the derivative? All right, so 3 can be taken out, and then x fourth becomes what? 4 times x cubed, right? Now, I'm going to go ahead and write this all together because this is like the sum of 4 terms, and the derivative of a sum is the sum of the derivatives, right? So I can just differentiate term by term. So 3x to the fourth becomes 3 times 4x cubed minus, now x cubed becomes 3x squared. 5x becomes what? 5 times the derivative of x, which is 1, so it's just 5. And then what happens to negative 26? Constant just disappears. Okay, it just vanishes. Gone. Nice, right? All right, so the derivative is 12x cubed minus 3x squared plus 5. All right, so remember I said a few sections ago that, you know, within a couple of days, you do not have to take limits as h approaches 0 anymore, that you will be able to figure out the derivatives very quickly. And this is what I was referring to. So now you have these wonderful tools, 4 tools to use in order to differentiate. So we have talked about the sum and the difference and the constant multiple. So what about the product? What about quotients and products? Well, that actually turns out to be a little different story, slightly more complicated. So we'll cover that in the next part or the segment of the video for section 3.3.